Hi, I just thought I'll do a short video, follow-up video on the capacitance question during the for the trial exam. Right, this is the question. In this question, it states that there is a circuit with a capacitor as shown in the diagram. Right, essentially what this portion is that it is a constant current power supply to charge a capacitor. Right, it writes here the rheostat is manually adjusted so that the current in the circuit is kept constant, right? And then we are asked to plot a variation of PD voltage across the capacitor with time, right? So this is exactly what I have set up today. This will be my simplified, overly simplified circuit diagram. What I have here is a power supply, right? This power supply can do constant current mode, as in it will only put out a constant current and vary the voltage accordingly, right? So I have two capacitors here in parallel, two capacitors because the larger capacitance allows me to plot the voltage over a longer time, right? I have my oscilloscope set up to probe at these 2 points, right? I'll explain what this resistor is here for later. But as of now, I'll show you what happens when we charge this capacitor on the oscilloscope. So this is my setup. I have a oscilloscope, right? It is connected across my two capacitors here that I have joined in parallel. This is my power supply, all right? And this is the resistor with another probe across it. So let's take a look at the power supply first. The power supply, I've set it to 16 volts at 10 milliamps, right? 16 volts at 10 milliamps. So these are limits. So that means it will only go up to 16 volts and a maximum of 10 milliamps at any time, right? So it will just provide us a constant current source. All right, so now everything is set up. So let me just take a single snapshot here on the scope. Right, I'll turn on the power supply. And we should see that the voltage is rising across the capacitor linearly. So that's a straight line all the way up until 16 volts. Right, you can go in there and count the divisions if you wanted. It is at 2.35 volts per division, but here you can just see the voltage here on the power supply, 16 volts. Right, so a straight line charging across the capacitor when you have constant current power supply. Right, just to prove that the experiment is not flawed, I shall proceed and charge the capacitors now with a non-constant current power supply, as in I will just give it 16 volts all the way. Do not limit the current flowing to the capacitors, right? So by doing, to achieve that, I'm going to change the setting on my power supply. I'm going to raise the limit to 20 amps, right? 20 amps is a very large amount of current. So it will effectively have a non-capped charge rate, as in it will just allow as much current as it needs to charge the capacitors. Let me set up my scope here. Turn the time base down to say 50 milliseconds. Right. Recentering. Right. Set up for single shot. Oops, forgot to turn off this power supply. Right, now that the apparatus is set up for this is non-constant current charging. Right, turning on the power supply. There. This is when we do not have, come on, focus. Well, my phone's not working with me. So this is what happens when you charge capacitors at non-constant current, right? It has a curved shape, right? What we're looking at here is, of course, qualitatively, not quantitatively. I cannot tell you what is the exact curves and all because this is just a very simple, sloppy experiment. You see here down in the bottom of the range that there is a portion here, focus, that is rather straight. Right, that is because this power supply was still limited to 20 amps. So that gradient there still represents 20 amps of charging. And then this is when the current starts dropping off, right? Due to it being harder and harder to push charge to accumulate on one plate. Oops, I have adjusted the 3, 5. Right. So about that resistor I mentioned earlier, the resistor in the circuit, 0.1 milliohms, 0.1 ohms, sorry. Okay, this is for me to calculate the current, to show you that there is the current waveform across the circuit, right? By using Ohm's law, we can find out what is the current. Of course, we are just looking at this qualitatively, not quantitatively. So the values is actually irrelevant, just to show you the waveform, right? So by probing across the resistor, right, we can, with a fixed resistance value, we can calculate the current that's flowing through the resistor. And that's what I have set up here on channel 2 of the oscilloscope, right? So channel 2 will be measuring the current voltage drop across the resistor of a fixed value, right? So I'm just going to set this up now. Let's take a single shot again of the setup. Right. So the line in yellow is still voltage, and now I have the line in blue, current flowing through the circuit. As you can see, this is exactly what we expect to see. Voltage that drops off, in decreasing, increasing gradient, right? Decreasing, increasing gradient. And over here, it's what would this be? This would be a decreasing, decreasing gradient, right? It starts off very high current, very, very high current, right? I said it's very easy to push charge into the capacitor. Then as it becomes harder and harder to push charge, the effective impedance of the capacitor increases, so the current drops off as the voltage increases. Right, that's all. Thank you for watching.